Hello, everybody. We are Group 18, and our project is GPMS, a Generative Projection Mapping System. My name is Francisco Soriano, and I am a computer engineering major.
Hi, I'm Victoria Moreno, and I am a computer engineering major.
My name's Declan Carter, and I'm also a computer engineering major.
First, we will give you an introduction to what GPMS is, along with our goals and objectives of our project. Then, we will give you all a system overview of GPMS, and then our initial prototype, which will then bleed into the specifications of our project. Finally, we will finish it off with administrative content and closing remarks. So our motivation begins with passion, where each of us have a passion for immersive storytelling, which directly led us to a wide interest in how to combine this with projection mapping, taking it all to the next level. So our proposal for this passion was GPMS, a portable system that leverages generative AI for themed projection onto any structure, such that the projection would wrap itself onto the structure's features. And as you all may or may not know, the projection mappings that Disney makes onto their large castle inspired and fueled our team because we believe that we could bring those projection capabilities to everyday people like you and I. This motivation gave us a hopeful opportunity to begin drafting what it would look like to pitch this idea to select entertainment venues who do not have this generative AI projection mapping capability just yet, once we finish finalizing GPMS, of course. A quick use case on a smaller scale would see GPMS being used at a birthday party venue where the theme is cat eating donuts. This is where GPMS comes into play, because it has the generative AI capability to project any theme, including cat eating donuts. In a holistic view, our project is to make projection mapping accessible to everybody using generative AI.
Introduce GPMS, our Generative Projection Mapping System. GPMS is a system designed to transform any physical structure into a canvas for AI-generated art. It consists of a Raspberry Pi connected to a touchscreen display, projector, and camera. The user starts by calibrating the projection area via software and aligning the projector's field of view with the target structure, as shown in the animation above. Once the alignment is complete, the system captures an image, which is then sent to our custom generative AI server. The server processes the image and generates a stunning picture that aligns with the key vertices and edges of the captured structure, as demonstrated in the animation below. Our basic goals and objectives for the project are as follows. First, we want to accurately project an image onto a structure using computer vision. This means making sure the key parts of the image, like its vertices, line up with the features of the surface we're projecting onto. Next, we aim to make the device easy to use. The touchscreen interface should let the user interact seamlessly with the system. After entering a prompt, they should see a relevant AI-generated image that matches the shape of the structure and fits naturally onto the surface. Finally, we need to make sure the GPMS has enough power to run reliably throughout its operation.
Now, our advanced goal is to give users more control over the generated images based on their input and preferences. This can be done through two objectives. First, by allowing users to specify two threshold values through input sliders, which will be used to fine-tune the outline of their structure. And secondly, allow users to specify their image style, like animated or realistic.
The stretch goals include user highlighting, a more streamlined experience, and an advanced power supply. First off, the stretch goal of user highlighting is aimed to create an intuitive interface that lets users easily select and emphasize structural features, offering a more personalized visual experience. Users could then easily choose features directly on the structured image, ensuring close alignment with the selected elements. Secondly, a streamlined experience revolves around the plan to integrate automatic calibration to adapt to structural features with minimal user input, which ensures optimal image display with a simple setup. Lastly, the advanced power supply stretch goal would be to design a PCB that houses a buck-down regulator that meets the specific voltage and current needs, adjusting the power supply unit's output for the GPMS system. Therefore, our objectives include creating a user-friendly front-end for highlighting structural features, implementing automatic device calibration for structure features, and designing a custom PCB with a buck-down regulator for the voltage and current adjustment.
As you can see, we have several categories of specifications. Size. Our target dimensions are 7 by 10 by 8 inches, ensuring the device is compact and portable. Weight. We're aiming for a weight of less than 10 pounds, making it manageable for users to handle and transport. While these specifications are important for the overall design and usability of our device, today we'll be focusing on measuring and discussing the last three specifications highlighted in yellow. First, elapsed time. Our target is less than 5 minutes for the entire process. 2. Alignment accuracy. We're aiming for less than 8 millimeters of offset from our projected image. 3. AI generation time. Our goal is less than 1.5 minutes per image. These three metrics are crucial for ensuring the efficiency, precision, and speed of our GPMS device, which directly impact the user experience and overall performance of the system.
Now, time for a hardware overview. The hardware components of GPMS are meticulously integrated to ensure seamless functionality. At the core of the system lies the single board computer, the Raspberry Pi 5, which serves as the brains of GPMS. The Raspberry Pi is powered by a 5-volt wall outlet AC converter that provides the required 5 volts at 3 amps, ensuring stable operation. This foundation sets the stage for connecting and powering the other essential components of the system. One key interface is the touchscreen monitor, which allows users to interact with the system. The monitor communicates with the Raspberry Pi by sending input data through a USB connection and receiving image data via HDMI. Complementing this setup is the camera module, which connects to the Pi through the serial camera interface. The camera captures images and sends them to the Pi while drawing power directly from the Pi at 3.3 volts and 250 milliamps, streamlining the system's power requirements. The Raspberry Pi 5 utilizes Wi-Fi to connect to a local server, where it uses TCP/IP protocols for reliable communication. Through this connection, the Pi sends image data to the server for AI image generation and retrieves the processed images. The processed image data is then transmitted via HDMI to a projector, which is powered directly by a wall outlet. The projector displays the AI-generated images onto the desired surface, completing the system's image generation and output process. The bulk of the hardware components are housed in a custom-designed 3D printed enclosure made from PLA filament. This enclosure was thoughtfully crafted to securely hold the touchscreen monitor, Raspberry Pi 5, and camera module. Mounted on the projector using Velcro for stability, the enclosure prevents unwanted movement during operation. The design includes precise dimensions to accommodate each component, with the touchscreen monitor embedded flush at the top and the Raspberry Pi 5 securely fastened to the enclosure's base. The camera is mounted above the projector lens using screws and nuts, ensuring proper alignment parallel to the lens's plane. To enhance usability, the enclosure is designed with cable management in mind. The touchscreen monitor hides most of the cables, reducing visible clutter, while a side opening allows external hardware cables to connect seamlessly to the Raspberry Pi. This thoughtful design not only simplifies hardware integration, but also ensures a clean and professional-looking appearance, making GPMS an efficient and user-friendly system. The table compares three computing options: microcontroller units, development boards, and single-board computers, focusing on functionality, complexity, and pricing. So MCUs are priced between $1 and $10 and are designed for simple tasks and do not include an operating system. They require custom PCBs in order to connect peripherals, making them less ideal for projects needing advanced user interfaces, display ports, or complex software frameworks like GPMS. Development boards priced between $10 and $30 offer moderate integration, complexity, and basic peripheral support. However, they do lack a full operating system, which limits their functionality compared to the single-board computers, but they are suitable for simpler projects without the need for extensive software. And single-board computers, like the Raspberry Pi 5, priced at around $60, provide powerful processing capabilities and run a full operating system, typically Linux. They are ideal for projects requiring advanced GUIs, high-quality graphics, and complex functionality, all supporting the easy integration with peripherals like cameras and displays. The key takeaway is the Raspberry Pi 5 is the best choice for GPMS, offering the power, OS, and graphical capabilities necessary for sophisticated software projects and interactive applications. For the GPMS project, we needed a touchscreen technology that was both functional and user-friendly. After evaluating resistive, capacitive, and infrared touch options, we chose a capacitive touchscreen. For the GPMS project, we needed a touchscreen technology that was both functional and user-friendly. After evaluating resistive, capacitive, and infrared touch options, we chose a capacitive touchscreen. Capacitive touchscreens respond to electrical conductivity, offering multi-touch support and clear visibility, which are features crucial for our user interface. While resistive touch is less expensive, it does lack the multi-touch capability and has reduced clarity. Infrared touch provides good multi-touch support, but it is the most expensive option. Capacitive touch strikes the perfect balance between functionality and cost, making it the most suitable and optimal choice for our project's user interface needs. After comparing Bluetooth and Wi-Fi, we found that Wi-Fi was the clear choice for several reasons. First, Wi-Fi offers significantly higher bandwidth, making it ideal for handling the large amounts of image data generated by our system. Second, Wi-Fi integrates seamlessly with a client-server model, which is important for scaling our project's functionality to users in the future. Finally, Wi-Fi provides overall ease of integration, reducing complexity in both development and deployment. While Bluetooth is suitable for some applications, its low bandwidth and lack of optimal integration would limit our system's performance. In short, Wi-Fi was the most practical and efficient solution for our needs.
The GPMS application consists of three main components working in harmony: the main loop, the computer vision module, and the AI server. Let me first explain the overview of the entire application, and then we'll dive deeper into each part. When you launch the app, you start with camera calibration. This crucial first step accounts for camera distortion and defines the projection area. Once calibrated, you set the edge detection thresholds in the computer vision module. These thresholds determine how the system identifies edges in the projection space. Next, you input a prompt describing the image you want. Your prompt, along with the processed surface information, is sent to our AI server. The server generates two unique images using Stable Diffusion technology. Finally, you choose which AI-generated image to project, and the system maps it perfectly onto your surface. This seamless integration of computer vision and AI allows you to create custom, context-aware projections with just a simple text prompt. Now let's explore each component in more detail. The main loop is where users primarily interact with the system. The process begins with camera calibration, where users select the corners of their desired projection area. Next, they adjust sensitivity thresholds for edge detection. The system then projects the edge-detected image onto the surface, allowing users to verify proper calibration and alignment with the structure's edges. Once satisfied, users input a prompt and choose a photo style. The application automatically sends this information along with the edge-detected image to the server. Upon receiving two generated images in return, users can select their preferred one for projection.
We start by projecting a calibration image onto the surface, illuminating and providing clear bounds for viewable edges. In this case, we utilize a plain white image to ensure maximum and equal coverage over the surface. No matter what angle or position GPMS is in, the system utilizes the input boundaries of the projection area and adjusts by warping the camera image to fit the surface. After the scaling, we run edge detection to ensure proper calibration, projecting the detected edges back onto the scene, allowing the user to take further steps to fine-tune the boundaries. Next, from the main loop, we send a still frame of the surface, along with user's prompt and any relevant metadata, to our custom generative AI server. The machine itself is running a Python server, allowing incoming HTTPS post requests to its API endpoint. Upon receiving the data, the server enhances the user's prompt by filling in any omitted details. It utilizes the user's selected style to apply predefined expansions that are optimized to that specific style, in this case animated or realistic. Additionally, the server configures a control net to guide the Stable Diffusion model, specifically Stable Diffusion XL. Control net performs edge detection on the input frame and ensures that the prominent edges and key features of the original surface are preserved throughout the image generation process. Stable Diffusion, at its core, is an advanced AI model designed to generate images from textual descriptions. It operates by initiating with random noise and progressively refining this noise into a coherent and detailed image through iterative processes. ControlNet introduces a significant enhancement to this functionality by incorporating reference images as guidance. As demonstrated in the examples provided, a simple sketch of a door, composed of basic lines, can serve as a structural reference. ControlNet leverages this input to produce various door designs while preserving the fundamental archway structure depicted in the original sketch. This capability is integral to our approach for accurately projecting generated images back onto the original surface. As illustrated in the accompanying technical diagram, ControlNet employs a locked copy of the initial structure to ensure the generated image aligns precisely with the original edges and positional data. This meticulous alignment makes it an ideal solution for projection mapping. When developing the tablet application for the Raspberry Pi, we considered several frameworks. Electron, based on JavaScript, is highly accessible for web developers and simplifies UI creation. However, it requires additional libraries for OpenCV integration and lacks the native performance of C++ frameworks. Flutter, using Dart, offers high performance through native, compilation, and smooth UI experiences, but also needs extra effort for OpenCV integration and multi-touch functionality. We ultimately chose Qt, a C++ framework with built-in OpenCV support, offering high performance, robust multi-touch capabilities, and strong community support. Qt's cross-platform compatibility and efficiency made it the best choice for developing a feature-rich application. Pulled from our original prototype, we demonstrate how Stable Diffusion works with control nets. Imagine drawing alongside a child, and they create a fun, silly picture of a cat eating a donut. With GPMS, we can bring that image to life. The final image you see here is entirely generated by AI, using the simple prompt, cat eating a donut, along with phrases like realistic rendering and whimsical to guide the style and tone. Another great use of GPMS is decorating your home. Imagine hosting a Christmas party, but wanting to skip the hassle of traditional decorations. With GPMS, you can easily transform your space using AI. For example, this final image was generated entirely with simple prompt like suburban Christmas party with candy cane inspired paintings and festive colors. One of the first aspects of our proof of concept we tackled in Senior Design 1 was implementing camera calibration. To do this, I wrote a Python script allowing users to select the 4 corners of the projection field. This is our initial approach for handling camera calibration manually. Next, we added a simple canny edge detection method to the original script. This allows us to precisely match the features and vertices of our projected image onto the final surface. As you can see in the example, it captures and aligns with the semi-random pattern of the cloth, ensuring accurate projection. Again, these examples, with the exception of the following GUI walkthrough, are only representative of our initial prototypes, with clearer depictions of the final project in our final demo presentation.
We'll now walk you through our GUI interface, which users interact with at a click of a button. The user begins by reading a few simple steps that explain the process before starting their vision. Once they understand their task, they'll move on to the calibration page where the camera turns on, allowing them to select 4 vertices to capture their target structure. After capturing the structure, users proceed to the sensitivity page, where they can leverage canny edge detection to fine-tune the structure's edges to their liking. They'll then input a prompt, just 1 to 2 sentences describing what they envision for their final image, which sends a request to our server. The server returns 2 AI-generated images based on the user's prompt, from which they'll select their preferred image for projection. Finally, users will see their earlier captured structure with their chosen AI-generated image projected onto it.
There were various design standards that our group adhered to, each playing a crucial role in ensuring compatibility, performance, and reliability across our project components. HDMI is a high bandwidth standard for transmitting high-definition video and audio via a single cable, ensuring simplicity and security, though it may face issues like connection failures and/or cable length limitations. TCP is a protocol that ensures reliable and accurate delivery of data between devices, making it essential for applications requiring high data integrity like GPMS by dynamically managing those packet transmissions. SSL is crucial for establishing a secure HTTPS connection between the client and server within GPMS. The use of a self-signed SSL certificate ensures that data integrity and confidentiality are maintained during transmission, essential for protecting sensitive information, such as API keys, from potential interceptions on the university's network. Camera standards include ISO for image quality and ratings for durability, ensuring that the camera meets performance and environmental needs for the project.
There are several key design constraints we faced with GPMS. First, we aim to minimize costs during prototyping to keep expenses manageable for our group. Additionally, we'll focus on reducing the final product's price to make it more accessible for everyday consumers. Another challenge has been time constraints, largely due to the administrative tasks and integration issues having taken longer than expected. We're also mindful of ethical considerations, such as implementing safeguards to prevent inappropriate content from being generated on our system. Lastly, since we're using a machine that was gifted to us and is connected to UCF's network, we've taken extra precautions to ensure the security of both the machine and the UCF network. The table of work distribution is as follows, with an equal and fair distribution over the 6 main components of GPMS, including PSU/hardware integration, computer vision software stack, UI design interface, generative AI pipeline, administrative contributions, and prototype design.
The bill of materials is in the table, with the bulk of the cost being derived from the AMD machine, which we actually have granted access to, meaning it is of no cost for us to use it. The projector, monitor, camera, and Raspberry Pi 5 collectively make up our total cost of $219.62, which will be evenly split at the end of Senior Design 2. The GPMS pricing for users would not include the full cost of the AMD machine. This machine functions as a central server supporting all GPMS products, providing shared resources and capabilities across the product line.
Thank you for listening to our presentation on GPMS. For more information, visit our website below.